HVAC 360 is brought to you today by the Commercial Demo Funhouse. Ever just want to blow off some steam at the job site? Do you think that those demo guys are living it up on Easy Street and having all the fun? Well, Demo Brothers Dougie and Donnie want to share the wealth and let you get those unhealthy pent-up aggressions out of your system. There are electrical rooms with cable tray and wiring everywhere. There are sprinkler rooms, and there's even a mock-up of an architectural office. Did you ever want to drive a skid steer with a hook around the floor, ripping down everything in sight? Well, all this and more can be yours without the cleanup. Reservations are required and team building events are encouraged. Just bring your angry eyes and your PPE. Discounts also available for those with union cards. Come visit the Commercial Demo Funhouse, where every day is Demo Day. Hey, welcome back. Matt Nelson here, your host for HVAC 360, helping you be the best and the brightest in the field of HVAC. Each week, I'm either sharing information and lessons learned from the field or talking with industry experts. But I don't stop there. I want everybody to encourage you to double down on your weekly helping of HVAC knowledge by hopping on over to HVAC360.com and join my growing community of people just like you. As an added bonus, you're going to be among the first notified of my free webinar series that is coming to the first part of 2019. We're going to be launching that probably here either in March, late March, or April. And each one of these webinars that I'm going to be putting on only have 100 spots. So make sure that you're on that first to get notified by being on the list. So it's going to be on a first come, first served basis. So what is up for this week? Well, I wanted to share some information about electrical basics. Gaining electrical knowledge has been a little bit one of those things that's been on my bucket list for a long time now. And there are some things electrically that I have just struggled with, that have been just kind of a constant struggle. I don't claim to be the smartest person in the room, and some of these electrical concepts just, I don't have them down. And I think a lot of different factors have played into kind of obfuscating and making these a little bit confusing for me. So I took some time and I dug down a little bit deeper, and I got some good information for you that I want to share. Also, I just want to make sure that you understand that today is just the tip of the iceberg, but I wanted to talk about electrical stuff from a mechanical engineer's point of view, and obviously, fair warning, I'm going to do my best here, and I'm going to try to point out areas where it may be a little bit shaky, but I encourage all of you to just use this as a starting point and go down your own electrical rabbit hole to find the information that's going to make you the best and the brightest. So here it is. Let's talk a little bit about fundamentals in general. I think a little bit of the fundamentals. When you talk about electrical stuff, there are conductors, and that's the wiring. Those are usually made out of metal. These are things that allow electrons to flow easily. So copper, aluminum, those are going to be the two basics that you're going to be running into in electrical, in the electrical world. And there's other things called insulators. I think a lot of us are probably more familiar with insulators than anything else. Insulating glass and rubber. Those are some things that, we get. So these are things that don't have a lot of free electrons. Now, one thing that I learned in college that was kind of, I don't know, I like to think it was a little bit useful, but it was along the lines of the right-hand rule. So electrical charge moving along a path creates a magnetic field, and the magnetic field in the direction of the airflow, you can use your right hand, no left-handers, a right hand rule. You can kind of curl your fingers. The curling fingers will replicate the magnetic field around a wire, and the direction of your thumb is going to be the direction of the flow. So, and remember that with alternating current, it kind of flips-flops back and forth. So the vice versa is true. You can flip your hand over, it goes the other way. All right. One other thing I'd like to point out, a lot with the fundamentals, a lot of people like to use the analogy of electricity being like water. Now, I think that's doing a little bit more disservice than it is helping. It kind of confuses me a little bit because it doesn't always apply. It's a great kind of teaching tool, but it has its limits. And when you get to those limits, it really makes things confusing, and it doesn't really. It's not a be all end all of a metaphor for learning what the electrical charge, electrical current, electrical flow is all about. So one thing I want to I'll start off with is the Hertz. Now, you'd be like, really? Hertz? Why? Why are you starting here? Well, I always wondered, this is one of the questions that I'm like, where did it come from? Now, Hertz, if you don't know, obviously cycles per second, that describes kind of the oscillation of the alternating current. So when you're generating electricity, you're going to have your stator, your rotor. The stator is going to be the part that doesn't spin, and the rotor is going to be the part that spins. And that's what creates this electrical current. Now, so the Hertz is really the result of the spinning rotor. So 60 cycles per second, that's where you get that's the kind of the rotation of the motor. Think about it this way. That's kind of also something that might be a little bit more useful. If you talk about RPM, so revolutions per minute, now you have 60 hertz and 60 seconds in a minute. So if you take 60 hertz and 60 cycles, or 60 cycles, 60 seconds in a minute, and you multiply those two things together, you get 3,600 RPM. Now, if you've known about motors and pumps and things like that, that's going to be a pretty familiar number to you. 3,600 RPM. Also, when you cut it in half, you get the 1,800 RPM. So if you've ever wondered where those numbers kind of come from, it's really about the hertz and where they are found in the world. So one of the questions, obviously, why 60? And if you're not in the U.S., Canada, it's going to be 50 hertz. Why 50 hertz? And I think there was a lot, when we started developing alternating current, I think one of the things that first came on the scene was the fact that we could, convert different AC voltages. So we had these transformers. So once we got the transformers, then we could start building these systems. Now these are kind of small systems. These are kind of test sites that popped up all around the world. Not just here in the U.S., but so the British inventors with the transformers, the Italians got on board pretty early with their alternating current system. Now, what did the Italians do? The Italians picked 130 hertz. This is, where did it come from? I'm not exactly sure, but, they actually scaled it down to 120 hertz. And they, you could see with a lot of these early systems, there was no, they weren't married to one specific hertz rating. So that they were playing around with it. In 1886, Westinghouse, who was the big alternating current proponent versus Edison, who was the DC proponent, he bought the patents from the British for the transformers. Now he wanted when he made a system, it was 133.33 hertz. So this is one of those things where it's all over the board. 1891, Germany had a system. They used 55 volts and 40 hertz. So you got everything from 40 hertz to 133 hertz, and everywhere in between. So where did we kind of settle on the 60 and 50? Well, I guess it's important to note is that in the early systems, the one thing that was very important was that you're going to be primarily using the electrical systems for lighting light bulbs. So what you couldn't do is supply the alternating current at too low of hertz, because you would see that it would pulse. It would actually flash on and off. Now, the one thing that so it had to be up there. It couldn't be, I'm sure it had to be above like 32 with the frame refresh rate that you'd see on a TV and the flicker. It's something similar to that. So it had to be above that. So I think, when Germany had the 40 hertz, I think that's probably the lower end. But you want to make sure that it was low enough, because there are idle losses when you start including motors, which was the other big use. The idle losses were less at the lower frequencies. But obviously, you had that lower limit where we had the flickering bulbs. Now, in 1893, Chicago's World Fair, Westinghouse was putting on a demonstration project. Now, here's a name that you're probably familiar with, or should be at least. But Nikola Tesla, he was working for Westinghouse at the time, and he decided to pick 60 hertz. Why? 60 cycles in a second, 60 minutes in an hour. 60 seemed like a good number for him. It was down, towards that lower end, but not too close. So 60 seemed to fit. So that's kind of the best explanation of 60 hertz that I've heard be explained. Now, why did the rest of the world go with 50 hertz? Well, when you're dealing with a metric system, 60 is not a great number. Different numbers that are better. 50 hertz is good. 100 hertz, that would be okay. So they had a choice, but I think they picked 50 because it worked. It was a nice metric number, a good metric choice, and it wasn't too high for those idle losses, and it wasn't too low to get into those flickering light bulbs. So 50 hertz was the metric choice. Now, the fact that we don't have these demonstration systems anymore, everybody is pretty much locked into those hertz ratings. So that's pretty much it. Except for the fact that I want to point out is what's the one fun and exciting thing about mechanical engineering and hertz is the VFDs. Yes, that's right. So we don't change the voltage, we change the hertz. So you have everything from running motors at half speed, which would be 33 hertz in the US here. And you would have, and there are also plug fans. Some of the plug fans, some of the fan wall systems, you can actually increase the hertz. So some of those run at 80 hertz or 90 hertz. It really kind of depends on the selection that you have. So keep that in mind with those specific systems that, 60 hertz isn't always the right number. Especially if you get locked into that thinking that 60 hertz is your answer, and you come to find that you're short airflow, and you look at your selection, you go, oh, wait a minute, no, it wasn't supposed to be 60, it was supposed to be 80 hertz, and then you're going to get the right airflow out of this fan wall system. So that's one thing about hertz and in relation to mechanical engineering. Now let's move on to the next component that I broke down is phases. Now, all these systems were single phase. It wasn't until the World's Fair that they actually introduced two phase, and that was the kind of the first time that they used. They were demonstrating motors, and two phase was perfect for that. So that was one thing. I'll now, as far as single phase goes, I think it's one of the things that is important to note, and that I find just absolutely amazing. When we talk about DC, we can actually this is probably more towards the electrons flowing kind of thing. Now, DC power, you're constantly pushing from high to low, high pressure to low pressure, so to speak, positive to negative or negative to positive, depending on which way you look at it. So you're actually going from a higher electrical pressure to a lower electrical pressure, and that's where the water analogy works. AC current does not, and now to note, electrons do not flow as fast as you think they do. They actually flow pretty darn slow. The electromagnetic force, when we talked about that right-hand rule, that electromagnetic force that kind of propagates along the surface of the electrical wire, that actually travels speed of light fast. That's really pretty instantaneous. But as far as electrons flowing, not so fast. AC electrons, and this is kind of, it helps you out when you're talking about the different systems that are in buildings. Alternating current, electrons vibrate. When you look at a sine wave, one of the things that always bothered me, I'm like, okay, you follow it up and it peaks and then it goes back down to zero and then you're negative, and I'm like, wait a minute, what does that mean in reality? Because that's one of the things that's always bugged me. But when you really think about it, when you think about the rotor and the rotor and the stator, and the positive and negative poles that creates, because it creates that magnetic force. So whenever we talk about magnets, they have a north and a south pole. So that flips up and down in a single phase or in an electrical field. So you're going to have positive and you're going to have a negative aspect. So electrons, as part of the AC system, move back and forth. They don't necessarily just continuously flow out, and that's where like on a DC, they just vibrate in place, and that's where you get that sine wave, and that's where you get the negative part, because it's actually coming back. That's really what it means, is that you have the electron going forward and you have the electron coming back. So that's how I visualize it. Now, the single-phase motor, the problem with the single-phase motor is for the light, it does great. It's purely resistance, but to get a rotation on a single phase doesn't work, because typically if you hook up a single-phase motor to just a standard single-phase power supply, it's just going to vibrate in place. It's not going to go anywhere. It needs kind of a kickstart, and they've made modifications to be able to do that. There's certain components that are in single-phase motors that gives them the kick they need, and once they get that kick, they're fine. They start spinning, and that's fine. The one thing, I guess, when you talk about the different phases, that's important as well as is single phase. The torque is not constant because you're going up, you're going down, so it's not constant over the amount of time. And the average power that you are actually generating is half of the maximum power. And what is that supposed to mean to you? Just understand. We're gonna talk about 2-phase and 3-phase power, those kind of powers, and that number is going to change. So just remember that the average power is half of the maximum power. And that kind of goes into the explanation of why we use 2-phase, 3-phase, etc. So now 2-phase, the first time I heard that was used was the World's Fair. I don't see that being used anymore. I don't know about you, but I just don't see it. In the 2-phase, you have the standard phase, that starts at 0, it goes up and down through the cycle, 360 degrees. And then you have a second phase that starts it either started at negative 90 or positive 90, depending on where you look at the. So it's 90 degrees out of phase. Again, that's great for self-starting motors. It actually does, because you have these two sine waves now. It does have constant torque. Now the average power that you have is actually 1.5 times the maximum power. So now it's kind of almost like you get twice the average power that you did with a single phase. Okay, so twice the average power. Two phase, the only problem is there's some problems with it when you talk about generation. I'm not going to get into that, but suffice it to say, there's a specific reason why we don't use two-phase anymore, and it has to do with transmission losses and voltage drops across transmission lines. So, three-phase, however, does not have that. Three-phase is the first time, and that's three phases. So you have, starting at 0, you have 120 and 240 through that 360 degree. So they're all 120 degrees out of phase. The one great thing about these is the phase vectors actually add up to 0 when you're talking about the current, and that's kind of important when you start talking about transformers, when you start talking about three-phase motors, and you know the benefits here is that, again, you have the constant torque. So 2 and 3 phase constant torque, even 4, 5, 6 phase all have constant torque. And the P average, the power average, is 1.5 times the maximum power. So we're actually getting more. It's greater than the maximum power on a single phase. So we get this additive effect. Now, you could keep adding things. There are such things as 4 and 5 and 6 phases, but they're just not used. And why is that? You still have all the benefits. Your P average would be greater than in 3 phase, but the problem here is that you'd have more components. You'd have more wires. You'd have more transformers. You'd have more switch gear. Everything. It would just be more of everything. So the benefits that we get are limited. To at 3 phase. 3 phase is basically you think of it as the lowest common denominator for all these benefits. So the benefits are marginal at 4, 5, 6 phases, and the downsides are much greater. So 3 becomes that minimum, minimally feasible lowest common denominator that offers all these benefits. So that's why we have 3 phase. We have single phase and we have 3 phase. 2 phase does not make the cut. So that's primarily what we're going to have in these different systems. So, and again, all these phases, when we talk about phases, it's either 120 degrees out of phase, and that doesn't matter whether you're talking about US or you're talking metric. Both the same as far as the phasing goes. All right, let's move on. Let's talk about voltage now. Now, voltage was one of those things that I didn't get a lot of information for. I know that when Edison originally had done some of his tests with the direct current, the one thing that he wanted is he wanted at the house, at the load, he wanted 100 volts DC. That was his kind of objective. The problem is that it would be the voltage drop between the generator and the load. There would be a voltage drop, so you have to generate electricity at 110 volts DC to be able to get 100 volts at the load in the house. So that's really the only thing that I could find that was why 100 volts. I think there's probably somebody way smarter than me or even a little bit smarter than me, could probably identify why we kind of focused on just that 100 volts number. Why was that the magic number? But that was kind of the best explanation to why we generate things at 120 volts. Ultimately, we'd want that 100 volts at the load. So higher voltages, the one great thing about the AC system is we could generate higher voltages, and then we could transform them at the load, because the downside of the DC system, the direct current system, is that you have to have generators about every mile. So it really wasn't that efficient. You have to have all these little distributed power plants around your neighborhood to be able to generate DC power to your house. So with AC, we were able to transform from a higher voltage to a lower voltage, something a little bit safer, so to speak. Electricity in the wrong hands is always dangerous, but it was a little bit safer. Less transmission loss, smaller wires. These are all things that are a bonus of using higher voltages. Now, when you think about voltages, one of the things that, mechanically speaking, the voltages are very important, and voltages and phases are very important because they talk about equipment compatibility. Can I use, because you're gonna end up in this environment, this system of 120 volts or 480 volts or 220 volts, 230 volts, depending on where you are in the world. You're gonna be in this ecosystem, and all your equipment has to fit within that ecosystem. So if I want to use a three-phase chiller and I only have single-phase power, that's not going to work. That's not going to be a great match in that ecosystem. So that's how you can think of voltage. It's just, what type of equipment am I going to be using? That's a lot of conversation that I have with the electrician. What kind of power are we going to have? What are we going to be able to use? So I could actually, on my schedules, I could actually make the right selections and put that down. Some equipment isn't available at all the different voltages. So that's another important thing to realize about voltage. Now, voltage here in the U.S., we have a single phase voltage. That's going to come 120. That's from the power plant. 120, 240. You get 240 because you add the two phases of 120. It's not exactly that, but I won't get into that here. But you can basically simply add those two phases and you get 240. So that is one of the things. But they're both single phase, so they're both in the same phase. Now, when you get into three phase, there is a less common 120 208 phase. And we'll get into that when we talk a little bit about transformers. But you can get a 120 208 phase, three-phase system. But more commonly, the standard kind of commercial system that you're going to see in the U.S. is going to be the 277 480 volt. This is going to be your standard. Now, not everything, it's like, how do you plug in the outlets? Well, in a 277 system, you're not going to put that to an outlet. So what you have to have in those systems is you're going to have another transformer. You're going to have to transform down from that 277 480. You're going to have to transform down to 120 to get your plug loads. So that is kind of the downside of the 277 480 system. Upside, obviously, you have a higher voltage, which is better for big loads. And that was actually one of the benefits of the kind of this pseudo transition, this 120 208 three-phase, because you could take one of the legs and it would be 120. So you wouldn't need any additional transformers inside the building, but the maximum voltage you could get would be 208. So that was kind of the downside. Now, internationally speaking, here I'm a little bit, a little bit out of my realm, so to speak. But they have they had, I should say, a 220 380. Now that sounds like our standard system. The one thing that was kind of interesting that I noted in my research was that they still had like 120 volt, 110, 120 volt. That was the distribution system that was common in Europe pre-World War II. Once World War II ended, copper was at a shortage, and it was much cheaper. They could use thinner wire and still get the higher voltage. So since there was so much turmoil and change happening at that time, that's when they decided to actually kick it up. That's why it's 220 and now 230. That's why it's three-phase is like that. They don't have a single-phase system, to my knowledge. So, they have single phases, but their system is more of a three-phase, 50 hertz at 230 slash 400 volt. So that's kind of their standard. There's a 400 volt slash 690, but I'm not sure if that's kind of, there's a couple different voltages that were listed, like in Wikipedia, on 3-phase 60 hertz. We just don't use those. 600 volts, not a lot. All these are kind of considered too. One thing you got to realize, these considered, I'll use air quotes, low voltage. Low voltage when it comes to talking about power. Obviously, when we talk about controls, low voltage means something completely different. But what we're not talking about transmission type voltages here. We're just talking about, what we're going to use in the commercial environment, in the residential environment. So that's what we're gonna talk about. All right, I would love to anybody who wanted to explain, the different systems around the world. I'd be more than willing to entertain that. All right, so let's talk a little bit more about voltages. Now, when you talk about Hertz isn't going to vary. Coming from the electrical company, I mean, it's a spinning motor. You're going to get 60 hertz. Not a problem. Nobody's had any issues with that I know of. Who knows? I could be wrong. I have been before. But when we talk about the voltages I know can vary. And you get situations, especially you might get under voltage, you might get over voltage. But the electrical companies are very, very they're very, very cognizant, and they're very, very focused on getting you the right voltage. Now, typically, they can vary plus or minus 5%. So they can be 5% over, 5% under, and that's kind of what they expect to deliver to you. So that's what you'd kind of expect from them. So I guess a couple of things that you might think, depending on where you measure voltage, you might measure voltage in a system. So if it's outside that range, that might be an issue. As far as the utilization goes, where you use the power, there are specific minimum maximums as far as the pressure drop, or not pressure drop, the voltage drop rather. When you're talking about main to a sub panel, you can think have a max of 3% loss. When you go from your sub panel to your load, that's another 3% loss. But basically from the main to the load, the electrical code says you're probably going to have a maximum of a 5% drop, a voltage loss rather, for your system. So I guess if you measure, say for instance, if you measure the voltage at the main where it comes in, you could expect, again, that plus or minus 5%. If you measured it at the equipment, it would be plus 5%, but it might not be, it probably is not going to be any lower than minus 10. So 90% of what your rated load is. So the good thing is that most manufacturers really standardize around the plus or minus 10% of voltage. Now, that's the one thing when you take a look as a mechanical engineer, when you take a look at, say, you have a big motor in the U.S., a big motor, and it's like 20 horsepower. That's probably going to be a 460 volt. Now, a lot of times you specify it as a 480 volt, and that is kind of meaningless because that is more of a utility voltage and not a equipment voltage. The equipment voltage will be 460, and why is that important? Well, the equipment is rated at 460, so you get plus or minus 10% off of that. So that typically will fit within what your service entrance variation will be, plus your losses in the system. So that range, it'll be plus or minus 10%. As long as you can hit it within that plus or minus 10%, you're going to be okay. So that is kind of the reason why you see 460 volt on a like a 480 system. On a 120 system, you're going to see the 115, you're going to see 110. Those are kind of some of the typical voltages that you're going to see for equipment. on that system. And so that's one thing to understand is there's equipment voltages and there are service voltages. Service voltages are kind of, again, that kind of big picture, the ecosystem that you're playing in. But the equipment voltages are going to be less than what the system voltages are going to be. So you can get that plus or minus 10% and you're going to be fine as long as you're within that range. Now, let's talk a little bit about one of the last things I wanted to cover was transformers. Now, you have basically two different types of transformers, and it's probably, I might be stretching this a little bit. You might have to go on YouTube and figure out, understand transformers a little bit better. But again, this is simply, that was the one nice thing about one of the questions I really had in my mind is that, say for instance, at your residence, at your home, you're going to have some sort of transformer on a pole, and the system is going to be in a transformer. You have the wire coming in, and you wind it around the iron core, and depending on how many turns you have on both sides of your primary and secondary, because there's on a transformer there's a primary side and a secondary side, but they don't touch. That's one fascinating thing. So the one system for the electrical distribution doesn't touch your residential distribution for your house. Nor does it do that for any commercial project or utility project. That transformer physically isolates. And basically what it's doing is just creating a magnetic field. So on one side, you're going from an electrical current to a magnetic field. And on the secondary side, you're going from that magnetic field and inducing current in the wire. So that was the one kind of fascinating thing, and there are the different configurations. Why is there 4 wires on the Y transformer? Why is there 3 wires on the delta? I mean, where does that 4th wire go? And that's one of the things I probably maybe dedicate a special podcast, or maybe I'll save it for the membership group for where what is the purpose of the neutral? Because the one thing that really bugged me is, why is there a neutral for an outlet, but there's no neutral for a 240 load in your house? And that's one of the things. If I just said that and that kind of blew your mind, you need to figure that out, because that's really cool. Why there would be a neutral for 120 and not for the 240? Because I look at a lot of pumps, and I'm like, all these pumps, they have 3 phases, and they have the 3 wires going to them, and there's no neutral, and it just boggled my mind. I'm like, why is that? And it's the whole thing that all these the vector sums of the 3 phases, they all sum at 0, so you don't have you're kind of at any one time. Basically, the short answer is, and if this is confusing to you, I apologize, but basically at any one time, you're going to have one of those legs of those hot legs be actually more like a return, be the neutral, and it's going to rotate depending on what the phase is. So your 240 volt, you're going to have one of those phases is going to be the neutral, and it's going to that's going to complete the circuit. And again, this is all related to it's not necessarily flowing, it's vibrating back and forth. So as long as you've completed the circuit and you have that all the way back to the panel, all the way back to the transformer, and everything can vibrate back and forth, that's where the magic happens. So it doesn't necessarily have to flow in one direction, but it just it does this vibration thing, and that's kind of amazing. So why transformers? Why do you use Y transformers? Well, Y transformers are great because you end up getting 2 voltages out of it. You can go, because there is that 4th wire, which is the ground or the neutral. If you look at a Y, it actually looks like a Y, also called a star transformer or a star configuration. So the center is, it's all the same. It's at 0, and you can use that. But the distance between that and one of the legs, that's going to be 1 voltage, and from a leg to a leg is going to be a different voltage. So you have 2 voltages. When you talk about the 277 480, when you talk about the 120 208, those are going to be more than likely that's going to be a Y transformer, because if you get the smaller loads, that's what you want to have, because you're going to get those you're going to use some over here and some loads over here when you look at the panel, because the way they load the panel up, they're not always going to be the same, as opposed to like 3 wires, where if you're having larger loads with 3 wires, you're going to go to that load and it's not going to be unbalanced, because the load itself is balanced. But when you're using just a single phase off of the 3 phases, then it has a chance to become unbalanced. But the Y transformer is good for that. And it provides less torque, it's less efficient, which is the downside. But you really can't beat that 2 voltages just off the bat. The Delta doesn't have that. The Delta is good for high torque, more efficient, and you can have what they call a high leg Delta, which is like a different style. But typically, where you're gonna see these transformers, you're gonna see a Delta Y transformer. You have the Delta side, which is going to be the 3 phases coming from the utility, and you're going to have the Y side, which is going towards your loads, which gives you the 2 voltages, and that's really kind of where the magic happens. So hopefully that wasn't too confusing on the transformers. So that's that's pretty much it. I hope that was helpful. Thanks so much for listening. If you know somebody who's looking for more information about this topic, consider passing this episode along. If I've totally screwed something up and it wouldn't be the first time, let me know. Send me a line, Matt at HVAC360.com. And we'll start a conversation. I'd like to identify people who know a lot more about this than I do, because I think it's a fascinating topic. I think it's a topic that's oversimplified, and some of the explanations can go a long way towards making us better engineers. Again, if you're not a subscriber, consider joining the growing community over at HVAC360.com for some more weekly goodness, and I'd be greatly honored if you'd consider leaving me a rating and review on Apple Podcasts. All right, well, that's a wrap for this episode of HVAC 360. I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.